All right, my first question to you. How many inflection points do you see up there? Two? Okay, so like if I'm gonna move along the curve and you tell me when. No, don't worry about that little. That's just that's a glitch. That's the sim theory, and we're in progress or in action right there. Where do I hit an inflection point?
Right there. A little go back. Yeah, right there,
Right there. There's a good one, right?
Yeah.
Are you recording?
So there's,
Are you
I am recording, yes. So there's an inflection point, right? Okay, then where else? Tell me where else. Right there? Is the question? Okay, yes or no?
No.
How come no?
It's not continuous.
Okay, it's not continuous, right? Okay, how about we'll continue along. I beam up here. Right there, huh? Okay, possibly? Okay, no. No, and this is, it's not, I mean, it's kind of it's a point of discussion in any calculus class, because once again, this is just weird that this would be the case, but sometimes there's a little bit of confusion about that. You know, is it an inflection point or not? The curve is continuous there, and it is a place where we change concavity, right? But in my opinion, and I think this is pretty much generally considered to be true, it is not an inflection point, because this is our definition of an inflection point. A point where the graph of a function has a tangent line and where the concavity changes. So there's two parts of this, right? There's two really important pieces. Obviously, it has to be where the concavity changes. That's the definition of an inflection point. But it has to be a place where the function has a tangent line, right? Can anybody, now it's been a while since we talked about this, but can anybody tell me why that would necessarily be the case? Like, can you give me a cogent argument why that would need to be true? Yes, ma'am. There you go. Okay, because think where an inflection point is where we're changing concavity, which is a property of the second derivative, right? Okay. Well, think about, here's a good analogy. Where do derivatives not exist? Okay, the derivatives can't exist where the function doesn't exist, right? And they also don't exist at sharp corners and some other things. But they don't exist where there's a discontinuity in the function or where the function is undefined, right? Okay. So then, by extension, a second derivative is just a derivative of the first derivative, right? So wouldn't you extend that same relationship to the second derivative, right? Doesn't that make sense? Okay, so yeah, we couldn't have, there'd have to be a tangent line, because if there weren't a tangent line, the derivative wouldn't even exist there, right? So here's an example of a place where the function doesn't even, well, the function does exist there, but the derivative doesn't, because we have a gap in the function, right? And here the derivative does not exist because there's a sharp corner. So if the function that you're differentiating to get the second derivative doesn't even exist there, yeah, it would stand to reason that that can't be an inflection point, right? Okay? So we only get one in this case, and it's right there. That's the only place where the concavity changes, and we have, at the same time, a tangent to the curve. Tangent line exists there. Okay, so let's get a little more practice with stuff like this. On the assignment, there's two assignments up now over second derivative stuff. One of them is really just about concavity and kind of the shapes of functions, how the shape of a function relates to the second derivative, okay? The second one is the stuff I'm going to talk about today. The second one, which is actually a shorter assignment, I think it's only 8 questions, is where we're going to really use the second derivative test, which is a big deal. Okay, so let's look at a couple of these. It says sketch a graph of a function. There's actually, I kind of cheated on this one. It's 1, 2, 3, 4, 5, 6, 7, 8 questions in one. So the first one, you want to find the function that fits these criteria. The function is positive valued on the interval from a to b. the derivative is negative valued and the second derivative is negative valued. So first of all, can we cross some of these out right away?
Yes.
I mean, we can cross this guy out, how come?
Because negative.
Function's negative there, right? Function's negative there too, so those are done. Here the function's positive valued, but we gotta see if the rest of it fits. So if the derivative is negative, what's that telling us? Yeah, slope's negative, so that guy's out too, isn't it? Right? Does this one seem to fit then? It's function's positive, check. Derivative is negative because it's decreasing, check. Is the second derivative negative? It is. How come? How do you know?
It opens down.
It opens down, so it's concave down, right? And how do we know it's concave down? Because it's shedding water, or really our more mathematical test would be the tangent line sits above the curve there, right? So it's got to be concave down. Okay? So you get the idea, and you'll get plenty of practice with those. But that's one of the kinds of problems you're going to see. Okay, what about? Yeah, we don't need to do any more of those. You're good with those. And we did this yesterday. Okay, so now we're going to jump into second derivative test. So what this gives us, remember what the first derivative test is for. The first derivative test is something that we use in conjunction with our tables, and it's a way for us to determine the nature of a critical number. Is a critical number a minimum, a maximum, or neither, right? And remember how we do that. We just look at the behavior of the first derivative to the left and the right of the critical number by picking some test values, right? Okay, so we'll do this one maybe both ways, so you get an idea. All right, so in order to analyze this with a table, what's probably our first step? Let's kind of get back into that mode where we're going to try to fall into a procedure that we use to analyze functions. Okay, so first of all, let's check the domain, right? So where are we even going to be looking for critical numbers? What's the domain of a polynomial? All reals, right? So the domain's all reals. So then when we're making our table, we already know that for my first row, I'm going from negative infinity out to positive infinity. Okay? What else do I need to do then?
Then take the derivative.
Take the derivatives. Okay, so first derivative. What are we going to get for our first derivative? Ren, what do we get?
Negative 9x.
X squared minus 18x. Good. Okay, there's our first derivative. Okay? What can we do with first derivative?
Take the second.
We could. I mean, we're going to need to take a second derivative also. Let's go ahead and get that out of the way. So what is our second derivative? Minus 18, okay? So now we need some critical numbers, right? Okay, so what's going on here? Where are the, help me out in my search for critical numbers of the first derivative. Say it again. Set it equal to 0. The other possibility would be where it's undefined, but it's a polynomial, right? Polynomials are everywhere defined. So we're just going to set it equal to 0 and solve. So let's answer that question. F prime equals 0 when what? I mean, when this whole thing equals 0, right? But what can I do here?
You can take out a negative 9.
Okay, so we could take out a negative 9x, leaving me with.
X plus 8.
So what's that give us for critical numbers then?
0 and negative 2.
0 and negative 2. All right, so we get negative 2 and 0. And if we, let's finish our table up here. So we get F prime. What's going on at F prime there? 0. Okay, good. So those are zeros of the first derivative. I'm going to leave room for one more row this time. But that tells us down here at the bottom, if those are 0 derivatives, what does that tell us?
Says you're not.
Well, maybe. But only thing it tells us for sure, if the derivative is equal to 0 at those places, is what? But what about the topology of the shape of the curve? If the derivative is 0, what's that telling us? Horizontal tangent, right? So all we know for sure at this point is we've got horizontal tangents at those places, right? We don't know what's going on there. They could be minima, maxima, or neither, right? Okay, so let's just review the first derivative test. So how could we use the first derivative test to figure out what those are?
You would choose it.
Okay, test points? Okay. So what do you think? What are some good test points here? Help me out. So somebody who hasn't contributed, help me out. Johnson, give me what's a good test point? And remember, I'm just looking for places where I'm going to test the sign of the derivative around those critical numbers. So 1 would be a good one. So we'll pick 1. How about another one? 2. Well, 2. Okay, 2's, we already got 1. 1 is good because it's to the right of 0, right?
Negative.
So we say -1?
Yeah.
So -1's good. That fits in between those critical numbers. What's one more? -3. Okay, so we'll just test those. So we're gonna, and let's take advantage of the fact that we have the derivative in a factor form here already, right? So when I evaluate the derivative at 1, I don't care about the value, I just need the sign. Am I gonna get positive or negative sign? Negative, right? I'm gonna get a negative times a positive, right? So at that point, I have a negative first derivative. What about at -1? It's gonna be positive, isn't it? I'm gonna get positive times positive is positive, and -3. I'm gonna get positive times negative is negative, right? And so that tells me, the first derivative test tells me what then? I'm going from decreasing to increasing, so we can see that that's gonna be a minimum. And here I'm going from increasing to decreasing, so that's gotta be a maximum, right? Okay, so we got it. Okay, that's not bad. That works all right. But let's harness the power of the second derivative here. Okay, so the second derivative, I could factor out -18, right?
Yep.
So we could write this in factored form as -18 times x plus 1. Okay? So let's do something different here. Let's evaluate the sign of the second derivative at each of the first derivative critical numbers. This is the second derivative test. So what about, we had critical numbers at 0 and -2. What's the sign of the second derivative at 0? It's negative, isn't it? Okay, now think about that. Think about what happens if we add those two concepts up together, right? So I've got a 0 first derivative and a negative second derivative. That's a horizontal tangent line, and what kind of concavity? Negative, right? What's that have to be? It's gotta be a maximum, doesn't it? Right? If I get a 0 first derivative and a negative second derivative, concave down function with a horizontal tangent, it has to be a maximum. How about over here? What's the sign of the second derivative at -2? It's positive. So once again, it is 0 first derivative, so we got a horizontal tangent plus upward concavity has to be a minimum, right? And there's a really simple way to just kind of remember this quickly. If you get 0 first derivative and a negative second derivative, well, that's a sad function, right? You're frowning. If you get a 0 first derivative and a positive second derivative, well, that's a happy smiling function, right? So that's a minimum. Okay? So what's the advantage of the second derivative test there? Because there is a clear advantage.
It takes out weeks from
it's a lot cleaner, isn't it? Did I need to did you use any of those other 3 not previously necessary, but did I need any of those 3 test values? No, right? I didn't need any of that stuff. All I needed to do was work straight down in a column. I get the answer very quickly, right? Okay, see how that works? So there's a general rule here on these tables then. You want to work as far down the table as you can. The further down the table you work, the more bang for your buck, right? Because let's eliminate, I'm gonna erase these to show you how nice and clean this is gonna be. So once we get rid of these guys. Okay, so let's get some more stuff out of this. Working all the way down the table, are there any zeros of the second derivative? Where's the second derivative equal to 0?
Negative 1.
Okay, so the second derivative is equal to 0 at -1. We get something else here, just a freebie. So what is going on at -1 for sure? It's an inflection point. How come?
Because the slope of
The second derivative is changing sign. That's the definition of an inflection point, isn't it? Does that make sense? Okay, it's a place where we're changing concavity, and so here we get an inflection point. And look at all that information we get for free, right? I mean, we didn't do very much work, and that gave us an awful lot of information. If we wanted to anchor this and come up with a sketch, because that's where we're going with this. The next really big thing we're gonna do in here, we did related rates, right? And by the way, I've got tests available, people that need to do retakes on that, I've got tests available, so we gotta kind of start scheduling those. The next big thing we're gonna do is curve sketching, where you're gonna make a table and you're gonna come up with a sketch of a function, an accurate sketch of a function based on just the table. So we could anchor this with just getting a couple points from our original function. If I evaluate the function at -2, what do I get? So it's gonna give me, what's that gonna give me? -8, so 24 minus 36 plus 4, so I get some big negative value, don't I?
Yeah.
Right? So negative big number. So we know that we're gonna, when we sketch this thing, it's gonna be -2 down quite a ways, right? If I plug in 0, that's an easy one. If I plug in 0, I just get 4.
Yeah.
Right? So there's an ordered pair. Well, what does that number give me? 36 and 24, so that's 60, so -56. Right, so now I could make a sketch pretty accurately with this thing, right? I know that I've got, here's my x-axis. I know I've got a point up here at 0, 4, that's gonna be a maximum. I've got a point at -2, -56, way down here, that's gonna be a minimum. And if I wanna know the exact location of the inflection point, I could even plug -1 in, right? And then I've got my function that I know is gonna look like this. Right? And I could even, I don't really need it, I mean, what's the end behavior have to be based on that function? As I approach positive infinity, what has to happen? What's f of x going to approach as x approaches infinity? It's got to be negative infinity, because this thing can't turn again, can it?
No.
Or we would have had another critical number in there, right? And how can we show that on the table? Just a quick reminder. All we have to do here is just take a limit. The limit of the function as x approaches infinity, well, we would just look at the leading term, wouldn't we?
Yeah.
As x approaches infinity, I'm going to get a huge negative number there, so I'm going to get a negative infinity if I take a limit. Oh boy, that's the left side of the board, it seems to be very,
Well, that's about
very
the same
glitchy.
spot as the last.
Yeah.
I know, it is, I think it's right over here. The limit as we approach negative infinity would be positive infinity, wouldn't it? Right? Okay. All right. Let's try another one. You get the idea?
Yeah.
Okay? Oh, and I guess I
That was
forgot I had this. Well, we don't need. Okay, how about this one? Yeah, I think this will be a good one, I think. Yeah. Okay? So domains everywhere, right? Okay, first derivative. 3x squared
Plus 4x.
plus 4x
The entire funding of the IRA.
plus 5, good. And then, okay, so is that gonna factor when we wanna find the zeros? How you gonna know?
There are many
You can use the negative, or b squared minus four ac.
Yeah, if we check the value of the discriminant on this one, what are we gonna get? If I tried b squared minus 4ac, I'm gonna get 16. Well, actually, I'm getting something negative, aren't I?
Yeah.
Right? Equals negative number. So this has no zeros anyway, right? Has no real zeros, okay? So what's that tell us about what's that tell us right away? If there are no zeros, if the function is, the derivative is defined everywhere, right? And it has no zeros, what's that tell you about the function?
And it-
Yeah, it doesn't have any extrema, right? No maxima, no minima, okay? There's no places where the derivative is equal to zero, so there are no horizontal tangents. Okay, but, you know, so we already have that part answered, but let's go a little further. Let's look for inflection points also. What about the second derivative? Okay, so that one, there is a zero of the second derivative, right? So if we were to make our table, goes from negative infinity to infinity. No first derivative, critical numbers, but the second derivative is zero where?
Two-thirds.
Negative 2/3. Negative 2/3, I get a zero of the second derivative. How would I look for inflection points here? Just to test if that's an inflection point.
Two numbers that are
There you go. Yeah, I just pick numbers around that. So 0 and like negative 10 or something. What's the sign of the second derivative at negative 10? Negative, how about at 0? So it's an inflection point in here.
What's the third derivative?
Third derivative is the rate of change of the second derivative. It's not very intuitive though. It's hard, you can't really make a, I mean, the second derivative you can see visually. You know, it's, yeah.
How about you?
Third derivative doesn't really tell us much. I mean, it's hard to make that connection visually.
But it doesn't provide any.
Well, yeah, it's the rate of change of the second derivative, but it's
Like, third derivative is not.
not very useful.
Right.
Yeah.
Okay, I wanna pick, you know what I wanna do? I wanna make my own if I don't like this one either. So we're gonna do, okay, let's do this function. Okay, easy one. F of x equals x cubed.
Okay.
We know what this looks like, but let's use the table to analyze this, okay? Because there's a real important point to be made here. There are times when the second derivative fails, and this is one of them. And you'll see why. So domain's everything, right? Okay, what's our first derivative?
3x.
Second derivative.
6x.
All right, so if we make our table then, okay, what's our only critical number? 0. Everybody agree the first derivative equals 0 at 0? Okay, so we only get one critical number. and the first derivative is equal to 0 there. So what's that tell us about the shape of the curve? Horizontal tangent line. Okay, we know that for sure. Let's use the second derivative and test it. What's the sign of the second derivative at 0? It's 0. It's neither positive nor negative, right? So if the second derivative is 0, the second derivative test failed. It didn't work. We didn't get a concavity there, right? So how are we gonna, what are we gonna do? Yeah, we're gonna test points around it. So we'll test points at, how about just -1 and 1? And here's the rule. If the second derivative test fails, fall back on the first derivative test, okay? So what's the sign of the first derivative at -1? Positive. What's the sign of the second derivative? Okay, so then, is this a minimum or a maximum? No, it's not, is it? It has to be a point of inflection, doesn't it, right? So what's this thing what's the only way, now this is enough for us to get the shape of this thing. If the slope is positive here and positive here, what's the only way I could possibly draw this curve? It's gonna have to go like this, isn't it? It's positive on that side, I get a horizontal tangent, and it's positive on that side. Everybody agree? Because it can't turn anywhere else, I didn't get any other derivatives. Okay, could I have done the same thing from the second derivative? Yeah, I could have. What's the sign of the second derivative at -1? How about at +1? So it is an inflection point, isn't it? Okay. Concave down, concave up. Either way you slice it, it has to look like that, doesn't it? Okay? All right, so let's try a similar one.
For the military, doesn't do combination. Is all he trying to do? I said no. And then he just kept talking. No, he just kept talking. I said no. Man, I can do it.
I can't do firefighter, I'm really selling that.
What if we do x to the 4th? First derivative,
4x cubed.
second derivative.
12x squared. That's for some. I'm not going into the military direction. Yeah, that's it. Put some logo. So Rem would be a perfect belly difference. When you're in the FE 17, you're between 4.
Okay, domain's everything, right? Okay, so what are we gonna get? What's our only critical number again?
0.
0. 0 is a 0 of the first derivative, so we know that we get a horizontal tangent line. Once again, the second derivative fails, it has 0 value. But this time, take your pick. You could really either fall back on the first derivative test, or you could use the second derivative row. All the textbooks say you fall back on the first derivative test, so we'll do that. Not that it really matters, though. So if I pick test points at -1 and 1, what do I get for the sign of the first derivative at -1? +1? Okay, so that tells us that it goes from decreasing to increasing, right? So that tells us it's a minimum. How could we get that same information from the second derivative row? Would you agree it's positive everywhere?
Yes.
Concavity? So then, what does that mean? If the concavity is gonna be positive there and positive there, is this a little strange? That there's gonna be one point, because I could have picked any test point to the left of 0, couldn't I? Or to the right of 0. So, does that even make sense? That you're gonna have one point on the function that has a concavity of 0, but the point immediately to the left has a concavity that's positive and the right has a concavity that's positive. That's a weird concept, isn't it? Because doesn't the concept of concavity, I mean, this is, and I'm just throwing this out there as kind of an interesting discussion. Doesn't the very concept of concavity depend on the relationship between points and its neighbors? Right? How can you have something that has, you have one point on a continuous function where the concavity is 0, and then right next to it the concavity is positive? Right? I mean, doesn't that almost imply that this really is, I mean, that really is positive concavity there? Right? I mean, if you take a step to the right or a step to the left and you're walking uphill in either direction, no matter how small the step is, then that really does act like, that sort of implies that this is really just kind of a positive, right? So you could, my point is, you could even use the second derivative row here as a way of analyzing that function, but it probably is easier just to use that first derivative row, because it's, you know, it's unambiguously a minimum, right? Okay? All right, let's try, maybe we skip those, let's try a harder one, let's try one with a log. Okay, so this is an example of, this is the kind of problem you're gonna do on the first assignment. This is a good example. Okay. But let's try to do the whole thing here. Let's try to find, let's not just find concave up and concave down intervals. Let's find the whole ball of wax. Let's find inflection points, extrema, all that stuff for this guy. This will be a little challenging. So first of all, what's the domain?
Your
So you gotta think in terms of a log function first of all, right? What's the domain, what's the natural domain of a log function? Like if I were just, and let's just take a little, just remind ourselves what a log function looks like.
And then you're gonna
So what's the graph of a log function look like? Okay, good, so it's asymptotic on the negative y-axis, right? And then it crosses the x-axis where? 1, 0. And then it just continues on forever. So what's the domain? 0 to infinity, right? So the argument of a log function, whatever you're feeding a log function, has to be a positive number. Agreed? Okay? So then in this case, what am I feeding the log function? Well, that stuff right there, right? Everything in the red bubble has to be positive. Agreed? Okay? So if we solve that, 3x squared plus 1 is greater than 0. When's that true? Yeah, when x squared is greater than negative 1/3. But when's that true? For what real numbers is x squared greater than some negative number? All reals, right? X squared is always positive, or always not negative, right? So the domain then would be all reals. Does that make sense? Okay. Okay, so we got the domain. We could start our table. Let's go ahead and differentiate them, because these might be hard derivatives. We might need lots of room. So what's the derivative of log u? Good review. U prime over u. Good. Okay, so we're going to get, what's u prime? 6x divided by,
3x squared plus 1.
okay, good.
Oh, no.
So let's analyze that one real quick while we're at it. So where is that undefined anywhere?
Yeah.
Yes.
Where? Where the denominator's 0, right?
Yes.
But where's the denominator 0? Nowhere. Right? Can't be. The denominator would be 0 when x squared equals negative 1/3, which it can't be, for no real value. And we're doing real calculus here, calculus of real numbers, real analysis. Okay, so there's no place where the first derivative is undefined. So we're okay there though, right? No critical numbers. Where is the first derivative equal to 0? Well, the numerator equals 0, right? And that's when x equals 0. Okay, so we do get one critical number. What about the second derivative? So that's kind of unfortunate. We got a quotient here. We got to use quotient rule. So what's quotient rule? Low D high. Minus high D low. What's that?
6x.
Good. All divided by low squared, right? Okay, so what's that give us then? If we distribute and collect like terms, I'm gonna get 6 minus 18x squared, is that right?
Yes.
Everybody agree with that?
Great. 6 minus 18.
Because aren't I gonna get, I'm gonna get a 18x squared plus 6 minus 36x squared,
Yes.
right?
Yeah.
Okay. So then we could factor that, and that's gonna be 6 times 1 minus 3x squared. Is that right? Yeah. Over 3x squared plus 1 squared. So are there any places where the first derivative equals 0? First derivative is gonna equal 0 when that is 0, right? Would you agree? So when 3x squared equals 1? Okay, right? Which would be when x equals plus or minus square root of 1/3. If I just divide by 3 and square root. Okay? So now we got everything we need to do our table. So we had first derivative critical number at 0. Second derivative critical, well, I guess critical number. Places where the second derivative is 0 at positive 1 over root 3 and negative 1 over root 3. So that's a 0. Those two are zeros. Now look how nicely that sets things up for us. We can use, if we want to figure out where we have inflection points, we're going to have to pick some test points around the zeros of the second derivative, right? But we're killing two birds with one stone here, because one of our test points would be 0, which we're going to apply the second derivative test to anyway, right? So what is the sign of the second derivative at 0? The sign of the second derivative. That's going to be positive, isn't it?
Yes.
Right? Okay, so we can see that we're getting positive. And so what is the nature of that critical number? Horizontal tangent, 0 first derivative, positive concavity. So it's a happy function, right? Okay, then we want to know, are these in fact inflection points? So let's check and see. If we pick a test point out here like at 10 and negative 10, what do we get for signs of the second derivative? In both cases, aren't I going to get negative? Because look, on the bottom it's always positive, something squared, but on the top I'm going to get positive times 1 minus big negative, right? So I'm getting negative over positive. So negative, negative. So look, those are inflection points, aren't they? Right? And what's this thing look like if I take a limit? As x approaches plus or minus infinity, I'm taking a log of an infinitely large number, which is what? Infinitely large. Now it's getting there pretty slowly, but it's infinity. Okay, so did I leave myself? Oh, I did that time. So we graph that time. So if we wanted to sketch this thing, what's it going to look like? At 0, 0, 0, right? If I plug 0 in for x, I get 0. I get the log of 1, which is 0. So I get the point 0, 0 is a minimum. And then, what's the function gonna do from there? What's it doing there? It's gotta change concavities, doesn't it? Right? So it's gonna go through an inflection point on this side and start leveling out. It's gonna go through an inflection point on this side. It never really levels out when it slows down, right? Okay, what do you notice about the shape of that? Does it have symmetry? Okay, so going back to one of our much earlier conversations, could we have cut our workload in half here? Could we have done this test for symmetry on this guy?
Yeah.
Yeah. Right, what is the test for even symmetry?
If the negative,
Yeah.
you could have
F of negative x equals
half of
f of x, which it clearly does, doesn't it? Right? Because look, the only x you see in the whole thing is inside of an x squared, and so it doesn't make any difference if I'm plugging in a positive or negative value. When I square it, I'm getting back the same positive value, aren't I? So this checks the box for even symmetry. And so really, we could have just done everything to the right and reflected it over the y-axis too to cut our workload down a little bit, right? Okay, does that make sense? Okay, that's a lot more thing. We'll do more of these things. There's some more stuff we can add to the table. But now you have to admit, isn't that table, isn't that just so cool? That you can do all that stuff on that one little table?